So I think it's time to start. So welcome everyone. So it's my pleasure to welcome Sebastian van Strien, who will be talking about chaos in multi-agent learning. So so this is part of the track. So this is part of the special interest group at the Turing Institute on Machine Learning and Dynamical Systems. So there are different tracks there, and then one of them is the track on dynamics and games. And so Sebastian's talk is going to be part of a reading group. So this will be the first lecture, and then there will be other lectures that will follow in this track of dynamics and games, and it will be coordinated by Amef Hussein. Yeah, so he's here, and then he will be talking about the reading group after Sebastian's talk. Yeah. Okay, Sebastian, thank you. You can start. Yeah.
Thank you very much for giving me the opportunity to give this talk. This talk is really sort of a mixture of like a survey, but also my own take on the subject. So initially I wanted to give more like a survey, but actually 1 hour is really not enough. So I'm going to mainly talk about work which is joined with the people mentioned there, the setting that I want to kind of discuss is the one of a multi-agent environment, where people have sort of agents or players. They can take moves, and the traditional setting in the game theory would be that you have a payoff matrix, and in a single shot, the classical game setting, a single shot game, players can move or make a decision, and the classical setting is, well, what they do is they take a best response with respect to one player, and so Y is the position of the one player, and they choose the best response, and the best response is, well, you pick this position of the vector Y, and now you ask what is A of Y. So A of Y could, for example, be the vector 2, 3, 1. And then what would be the best response of this? The best response of this vector would be, well, you pick out the response. So the vector X, well, X prime, because that's the transpose. And so that would be the second unit vector, because this is the largest component of AY. So that gives you the best payoff. So it's going to give you the best payoff. And so the idea here is that you have this choice where X is the best response to the position of Y, and Y is the best response to the position of player A, which is X. And the pair XY is called the Nash Equilibrium, which always exists. And so a very classical example of this situation is, of course, the prisoner dilemma, where you have two players. The first player can choose the row, and the second player, B, can choose the column. And well, of course, the sad thing is that the first player thinks, well, whatever I do, I'm better off choosing the first row, because I can choose between 20 years or 8 years, so that's better, and 6 months or 3, that's better. So I choose this row, the first row. And the second player can choose a column, and he will also choose the first column. So they will end up with this here as a response, so they get 8 years prisons, instead of, if they were able to communicate, 6 months. And of course, this is the setting that's kind of the classical setting. But now what we will look at is repeated actions. So where players will repeatedly choose actions. And actions are typically unit vectors. You have to choose one or the other. You can't take a mixed action. But of course, what you can do is you can choose a probability vector and choose, according to that probability vector, your action. And we'll see that later on. And the examples of games are, for example, matching pennies, or iterated prisoner dilemma, or iterated donation games, which is more or less the same game, where the players can choose either to cooperate or not to cooperate. If they cooperate, they pay into a pot a contribution of C, and they have a benefit. And of course, again, we have this situation that you will both have a benefit. The Nash equilibrium will be to the fact, but in fact, they will be better off if they play this here, if B is bigger than C. So B bigger than C would, of course, mean that this would be the better outcome, but the Nash equilibrium nevertheless is this opposed to fact. Now, in fact, in the case of iterated donation games, there may be a different story behind this. And of course, you can you can see there's all kind of these tournaments and so on about iterated prisoner dilemmas, and that's a whole story in itself. Or you, for example, you have iterated paper, rock, scissor games, which of course kids play, and so on. And so we will discuss some of that. And well, there are a lot of algorithms kind of to learn how to play these algorithms or these games. And sometimes the players will know actually the actions of the other player, or sometimes they will only know not the actions of the other player, but only the payoff they received. And there's all different settings, and I won't really go into that in big depth because that's a subject in itself. But you have here different sort of learning dynamics, and all of them have tremendous kind of sort of literature about them. Fictitious play and best response I will start discussing. And the idea is you always play the action which is best. And reinforcement learning is something a bit different, where you keep track of the profit of each action and play the most profitable action more often. And this could be even if your opponent is like nature, where you're actually playing against somebody who's unpredictable, or maybe has no even payoff structure in mind and so on. And replicator dynamics is something that where your action is chosen according to fitness. And then a final thing is, which we actually won't really discuss very much, is no regret learning. And that idea is that you choose the action that you regret not playing more often in the past. So all these different games are interesting in their own rights. But what I want to do, the aim of this talk, is to give a partial overview of some of these algorithms. Now, ask also why a player might be better off playing these learning rules rather than Nash, because there is sort of often a kind of a bit of a thought about play Nash is the rational thing to do, but of course it is not. If you look at the iterated prison dilemma game, if you could have the 6-month prison sentence instead of 8 years, of course that's a much better outcome. And of course you have all kind of versions of that. For example, these donation games. And now what I also want to show is that the dynamics of these can be extremely interesting and unusual. Not the type that you usually encounter in dynamical systems theory. And in addition, I want to show that these algorithms, although they are rather, different, there are some kind of interesting relationships between them. Now, on a different note, I teach an MSc course at Imperial College on this subject, but this talk is not a survey of that course and does not give a full overview of the entire research area. That would be far too much. So I will just choose to talk about some of my pet subjects. And, as Boumediene mentioned, this is the first talk in a sequence of talks organized by Amal. And other talks that will follow will also be Georges Pouliouas, who has also beautiful results. And I won't really discuss them here because I think that's sort of going to be too ambitious. So what I'm going to do now is to talk about fictitious play dynamics first. And there, in fact, the idea is very simple. The players have, they can play actions all the time. These are the actions. And what you do is you keep a track of what the players have done in the past. So you build a model of your opponent's play by just looking at the average action. So this could be the first unit vector, and then the second unit vector, and then this would be some average of those. So that would be some probability vector, and not a unit vector anymore, not 1, 0, 0 or something, but one. And of course you have also the continuous time where you instead integrate. And fictitious play is very simple. You choose every time the action that's the best response to your your model of the play of the other of the average of the other player. That's your model, and this is your response. and the BT also like that. And as before, the best response was the vector that will make this the largest. And of course, this can be multi-valued. For example, if you take the vector AY, if AY happens to be the vector 1, 1, 0, then of course, E1 and E2 both will give you the same output, the same payoff, namely 1, or some linear combination, a convex combination of them will give also that output. So what does that lead to? Well, that leads to actually a differential equation, at least in the continuous time, and in the discrete time, something a bit similar. So so what happens is your probabilities of playing actions. These are the probabilities that you choose these actions A and B will evolve in this way. So this is the way they evolve. So that's a best response minus X. So this is the difference between these two, and then 1 over T, because it's a learning model if you take it in the way that I described it before. So your speed will decrease because you're learning less and less. And so that's why this factor 1 over T appears. But there's also a different interpretation of the same, where you take the best response dynamics, where you're moving towards your best response. And this is what will happen in that case. So I'm going to draw that here. So here is the state space for the first player, the state of probability vectors in the R3, if you have 3 actions. So this is the 3 actions. And so this is some mixed action, and this is where we start. And for example, here you start. And if you're here, both players will move to this corner. And so they move here. And as soon as this player crosses this dashed line, the best response will switch from going to the third action, which is this one, to the first corner. And so the other player will have the effect that they choose a different direction, because it's this player, so they notice that this one is on the indifference line, so it's multi-valued, and then as soon as it crosses, he or she crosses, you will move like this. So the solutions will be sort of piecewise straight lines. And well, let me just tell you a bit of history. So Robinson in the 50s showed that if you have zero-sum games, then you have convergence to Nash equilibrium. And okay, so this was very exciting at the time, and they thought, well, this was actually a good way for players to find out what the Nash equilibrium, how to play a Nash equilibrium. And then people tried to find many more games where they could show convergence. And in fact, they were not so successful. And in fact, Shapley later showed, for the rock, paper, and scissor game, that in fact, you get convergence to a periodic solution. Here I've drawn that, and beta is a particular parameter in a game that we'll discuss later. But the periodic solution is the one you converge to, which is this one here and this one here. And so, I mean, this is, of course, the state space is the space x comma y. So x is in a two-dimensional triangle. This is a two-dimensional triangle. So you have a four-dimensional space. And these are projections from the four-dimensional space onto two simplexes. And of course, you can take different projections, and then you wouldn't really see it like, you would get a different view of the same thing. In fact, you could get a view where this is a hexagon, the periodic solution, projected from the four-dimensional ball to a two-dimensional space. Now, for many economists, this was actually the end of it. They said, well, okay, these players, they're going to play periodically, they're going to realize this, and then say, well, okay, I better play Nash, because this is stupid. I really understand the pattern of the play of the other player. Now, it turns out this may actually, in some ways, smart, or at least seemingly smart, but actually it turns out that if players play this very naive, fictitious play or best response, then in fact, they turn out to get on average better payoff than Nash. So even though this is a very naive kind of learning method. Nash is maybe very sophisticated, and in fact it's often very, very difficult to find. But in fact, the players would be better off playing Nash because on average they will each be better off than if playing Nash. Now, there's a sort of a whole story to be made, a separate talk about this, but this is one of the key points I want to kind of highlight. And let me kind of just to put this in a broader context. This, of course, is not something that people are completely, game theorists are completely unaware of. Because, in fact, game theorists often also discuss other notions than Nash, which are maybe less known in the sort of wider community, which are kind of generalizations of Nash equilibrium. And I'm going to just briefly mention that because, this idea that in Nash is sort of like sort of like the great thing, perhaps is even in the game theory community very well understood to be kind of a fallacy. Because, for example, if you take this Battle of Sexes game, well, this is the payoff. If both players choose the first action, maybe you watch football, and here they watch tennis. And of course, one has a preference for playing football, and the other for playing tennis. But both are better off. They don't want to be watching different games. They want to go to the same game. But of course, one maybe prefers to go to football match, and the other to a tennis match. And if you look at it, the mixed Nash equilibrium, you can easily work that out. That's this thing here. And the expected payoff is 2/3, 2/3. But actually, what would be much more rational if you look at the, what this means, that they will play actions according to these choices, 2/3, 1/3, and 1/3, 2/3. And so there's a very good probability of a mismatch. There's a probability that the first player chooses this action, the second action, and the second player plus the first action, and the payoff would be 0. And that's precisely why the payoff is 2/3, 2/3, which is not so good. And that's why actually there are various other notions. And for example, there's this notion of correlated equilibrium. And that's actually that you say, well, actually players are not going to be allowed or kind of rely on an intermediator, a trusted intermediator who is throwing a coin and tells them, you better play either the first or the second one. And I'm happy to make take the coin and then you follow my guidance. And so this will actually lead to a better payoff. So that means with probably half the players both choose to go this one and half this one. And there is actually a notion, which I won't really discuss in detail, that whether something is really meaningful, whether trusting the mediator is actually should be trusted. So there's some kind of optimality notion here, which I won't go into a lot. And so there's a lot of notions which generalize this notion of Nash equilibrium. And it turns out that, in fact, these games, they, in some sense, the dynamics, they somehow kind of understand that. Or rather, there's a very intermediate, it's a very kind of simple way that this here, the dynamics is often not stationary. It doesn't converge to a point. It can, but for example, in this periodic case, it goes to something periodic. And this periodic orbit is in a set which is called the correlated equilibrium set. And this correlated equilibrium set is actually something which it kind of tries to say, well, suppose the players are having some kind of way of having an intermediator behind them, then in fact they can actually do better. And so this is actually sort of in the background of this, that yes, you have this Nash equilibrium, but you have other notions, and in some sense the good dynamics kind of understands these other things. So that's one thing that I wanted to mention. Okay, so that the optimality of a Nash equilibrium is not, it's not the case. You have really other often you can do much better than that, and even these very naive learning rules very, very often actually achieve that. So it's not so smart to play a Nash necessarily. Now, the other thing I wanted to kind of mention here briefly, just to kind of towards the game, the dynamics community, is that if you have a zero-sum game, well, then I mentioned already that in fact you converge to a Nash equilibrium. So, you converge to some kind of points. And well, you can think of the spherical coordinates, you have the radial coordinates that converge to this Nash equilibrium, but you have also the spherical coordinates. And now if you take the dynamics, as projected on the spherical coordinates, then in fact the dynamics turns out to be Hamiltonian. So even though you converge to the Nash equilibrium, there's this Hamiltonian system which is related to what happens in mechanical systems without friction, and in those systems frequently you have also kind of chaotic motion. Well, in fact, that's precisely what happens. There is this Hamiltonian system here in the background. So in fact, there's also some kind of reverse of this, which I kind of want to mention, Hofbauer conjecture, which is saying, well, if the Nash equilibrium is attracting, and if this Nash equilibrium is actually in the interior of your state space, then conjecturally, in fact, the game is a zero-sum game. And I think this is often considered a key conjecture in the subject, which is still wide open. But together with a PhD student of mine and Dimitri Tourav, we have some kind of partial version of well, which maybe even hints that this may not be correct, this conjecture, but this is not what we actually show. Let me just sort of leave that topic there. So let me now sort of just give you a flavor of what can happen in such a family. So let's take this family of games. So we have this family of games here, where we take these two payoff matrices, and there's a parameter beta in there. If you take beta 0, then the first player is trying to copy. It's always going to kind of repeat what the other one is trying to do, and the other one is kind of trying to move ahead. If this vector is 1, 0, well, 0, 1, 0, then in fact the other one will say, well, I'm not taking that one, but I'm taking the next one. So the best response of EI is always EI plus 1. So in that sense, it's this is why it's like a generalization of paper, rock, scissors game. And the state space, as I mentioned, was 4-dimensional. And so, for example, if you take a certain parameter 0.9, well, you can see here the play here. This is time in the horizontal direction, and here is the kind of the way the probability vectors are moving. Well, you can see it's rather chaotic. And if you project the solution from this 4-dimensional space onto the two subplexes, you see this kind of direction. And sort of just to kind of remind you again, the solutions here are sort of just, moving in straight lines. And as soon as this player kind of hits this indifferent line, you move here. And when beta 0, these are the regions where, you have the best response, going to the third action, the first action, and the second action, and for the other one. And as beta changes, the angle of these indifference lines are changing. And so, for example, when beta is small, then we get this Shapley orbit, which I discussed before. But when beta is much larger, chasing a slightly different parameter, you get something here. And there's this very kind of complicated behavior that happens along these indifference lines. This is one of these indifference lines. And so let me kind of formalize that a little bit more. So when beta is between -1 and sigma is the golden mean, then in fact you have this Shapley orbit, which Shapley already found, but here we show it also for a whole parameter range. And this attracts an open set of initial conditions. And when beta is past the golden mean, in fact there is another periodic orbit. And this becomes attracting when sigma passes some other number, tau, which actually can be explicitly calculated, but it's beyond, it's tau 0.915. And there is, it's like a saddle orbit between sigma and tau. And then if you are beyond sigma, you also have an additional periodic orbit, which is actually, if I draw this here on this line, it's kind of following on this indifference line. It's kind of here and then backs up. So it goes here and then it kind of backs up. And the other one is kind of like here. So it's following these indifference lines. And so if you plot it, you would just see these 3 prongs in one plane and the 3 prongs in the other one. This would be what you would plot if you saw this projection. But if you took a different projection, you would actually see a hexagon. And so this actually turns out to be a very important orbit for understanding the game. So, this says, well, okay, it's attracting when beta is between 0 and sigma. This would be the kind of natural thing. You just look at linearization type of things. Well, this is far from true. The periodic orbit is attracting. So would that attract everything? No, that's definitely not the case. For example, this Nash equilibrium, which I call E here, attracts actually a lot of orbits, and not just something like a cone or something, or a stable manifold. That would be kind of a natural thing. In fact, it would be it's something much more tricky. So in fact, what happens is there's sort of like a cone where you attract, but there's another electron on which you kind of attract. There's another cone. There's a whole counter set of well, at least a countable set of cones which are attracting. So once you're on this cone, you kind of cycle here. And if you're not on that cone, you go out. Well, this is, of course, something that you would never see in a normal, smooth dynamical system. So this is completely different from the usual thing. And now, of course, you could say, well, this is because the flow is not smooth. Well, actually, the smooth, it's not smooth, that's true, but actually it's continuous at the Nash equilibrium, at least when the beta is between 0 and sigma. So there's a lot of surprising and interesting things, going beyond the kind of usual realm of smooth dynamical systems. Now, the next point I want to make is that actually when beta is between 0 and 1, then in fact there's infinitely many different orbits, of cyclic play. What do I mean by cyclic play? Well, that the players choose actions, for example, action 1, 2, and then 2, 2, and then 2, 3, and so on. And so they have these actions, and of course, while the actions are being played, the probability vectors change, but these are the actions they play, and this is kind of periodic. And in fact, there are a lot of non-isolated periodic orbits. So in other words, there's whole sort of orbits here, and then another orbit which is kind of parallel, and another orbit like this. And so it's completely different from the usual time. And solutions hit the Nash equilibrium in finite time. And in fact, maybe the final thing I want to say about this slide is that you have whole horseshoes. You have, positive topological entropy, and you have horseshoes for this thing. And this can be actually shown rigorously. And well, conjecturally, there are no periodic attractors for this whole parameter regime. And that's certainly what the numeric shows. So this is all I wanted to say about best response in fictitious play. So first of all, you have strange dynamics. Well, zero sum is kind of related to Hamiltonian structures. But maybe the final thing, from an application point of view, that might be the most important thing is that complicated dynamics is good for players in terms of average payoff. So this is one thing, and I could give a sort of, much longer talk or several talks about this subject, but let me sort of give more of an overview of this. Now, the next type of dynamics I want to discuss is replicator dynamics. Well, what is replicator dynamics? Well, that's kind of written here. So it's like a growth function, xi dot is equal to xi with a factor, this factor, which is, well, it's saying what's the payoff if I play action I compared to the mixed action that I'm actually I'm in at the moment. And this is sort of the the kind of fitness compared to the average fitness. So this is sort of a trait, trying to, how to improve this. And this model is actually used a lot in math biology, but also in economics, increasingly. One model in which it's used is where you have sort of, RNA. And so you have different RNAs, and one RNA of I catalyzes the reproduction of another RNA. And this is sort of particular thing which is meant to be a model for how in the primordial soup, the RNA fragments were sort of growing and growing. And in this case, it becomes periodic if n is at least 5. So this is, one type of model. And just to give you a flavor of what can happen in this case, again, in a zero-sum game, you have some kind of Hamiltonian type of dynamics. You have these quasi-periodic motions, and if you project it, in a correct way, then you see this thing. Although this is projection, this looks like a knotted thing, but of course, it's not in a three-dimensional, but in a four-dimensional object. So it's not really a knotted trefoil, but it looks like that. But if you project it differently, you can see here this, the trace of this torus sitting here and here on the, the two triangles projected. And this is another view of something. For different parameters, you get also this kind of behavior, which is kind of, some sort of orbits here. So these are different type of behaviors. And now, in fact, the funny thing is that it's, although a lot of study has been gone into this, and in particular, if you have a one-player game with 3 actions, there's a complete classification of this actually due to Ziemann. But in the high dimension case, not so much is known. However, there's an interesting connection. And this connection is that if you take the time average of a replicator orbit, so the orbits we just saw, then actually it's a pseudo orbit. It shadows an orbit of fictitious play. So there's a very intricate relationship between the replicator dynamics and fictitious play or best response dynamics. So that's one direction, and that's due to these authors. And there's also a reverse direction, and that's work in progress, which is that if you have a hyperbolic orbit of a fictitious play, or hyperbolic set, in fact, then in fact you have also a hyperbolic orbit or a hyperbolic set. And this in fact implies also that in the games that we just saw before, these rock, paper, scissors games, where actually not very much was known rigorously, that you can actually show that the results that were obtained for fictitious play rigorously imply that you have some chaotic switching in the replicator dynamics. So in some sense, make a very precise version of the pictures that we had in the previous slides. So here we have sort of the first instance of these seemingly completely different dynamical systems and learning methods, and the philosophy was quite different. Still, there is a sort of a very intricate relationship. And so this is kind of the short summary I want to, for this particular thing. So there's this strange dynamics, and again you have this Hamiltonian structure, and again it turns out that actually complicated dynamics seems to be good for players in terms of average payoff. Of course, maybe that comes at the price, but it's nevertheless. So now I want to go to reinforcement learning, where the idea is completely different. The reinforcement learning is, well, again, players have a payoff, so B and A are the actions at the time t, and this is the payoff received at time t, and then you update some kind of score vector. It's almost like you have a scorecard, and you keep track of whether you won or lost the game, and this is your scorecard. So here there are 1, 2, 3, 4, 5, 6 actions, and this is your cumulative scorecard. And of course, there's different ways of doing that, and this is what I'm going to discuss here. So one of the scorecards, which goes back a long way, was by Cross, where you kind of look at your current scorecard, and then you look at your new score. And here's the action. So you update only one particular vector. So this is a number, and this is a vector. So you kind of update the payoff, and so you kind of move this, this direction that you pay off. So you move up that particular column in the payoff vector, and so of course this keeps the sum of the coordinates of theta to be constant. So that's your score vector. So that was shown in this histogram before, but this is the score vector at each time. And of course, there's another one, by Roth, where you kind of just add the score rather than sort of kind of keeping the sum constant, or some kind of memory loss thing, so that you keep forgetting a little bit what happens in the past. Or what is actually very well known is the Q-learning, where you kind of update here, and this is the kind of classical thing in the Q-learning thing here. And in a random environment, where you have some kind of station distribution, there's sort of a fixed point of this equation, which corresponds to a solution of a Bellman equation. But here we're going to look much more in the game theoretic setting, and we will actually ignore this random environment. And so we will actually, then this gamma doesn't play kind of any role anymore, and we may as well set it 0. So that's sort of a particular thing. So we have these several ways of choosing, updating these Q vectors. And well, here's again this update vector. Now, once you have this update vector, you can also say, how am I going to choose which action to play? And there's several choices. And actually, that's what I want to discuss now, how they make a huge difference. So one is to say, well, I'm going to choose the largest component Q. So that would mean just the column which is the largest, these two. But if you do that, it's sort of, you don't kind of explore your state space too much. And that's why people usually also have this exploration term, which is that you add this extra term here. So you take this convex combination of this largest component, and then with equal probability, all the previous actions. So there's a sort of definite reason why you want to do this and not take epsilon 0 here. And then another version is softmax, where you can say, well, I'm kind of taking all the vectors, and there's, I take these Q's, I take the exponent of them, divided by some number t. And then in order to make this a probability vector, I normalize it. And of course, if t is very close to 0, this kind of picks up the largest vector. If t is essentially infinity, all these numbers will be the same. And then you would actually take with equal probability all the different actions. So yeah, so let's sort of look what happens in the different models. So quite often what people do is, well, they have this alpha sitting here, which is kind of your learning rate. This is your time step. And now let's sort of try to kind of analyze, to get a more grip on this thing here, is what happens if you take small time steps, which is kind of, instead of taking 1, you kind of take delta t, and you could actually put a normalization factor here also, which I kind of removed here just for simplicity. And then the effect you get in the limit, if you take this time step going to 0, you get a differential equation. One of these two in these two cases. And these are, things that are, very well studied as such. But let's, or at least should be well studied as such. So let's just kind of go back to this prisoner lemma and see what happens in that case. For example, if you take this prisoner lemma game, so we have this matrix A, and B has a similar matrix, namely A prime. And you see here the first player A will choose this, he can choose the row. And the first row is better than the second row. And the second player can choose a column and will choose the first column. Well, or more generally, you might choose a more general matrix like this with these inequalities. And well, because the first row dominates the second row and the first column, the second column, the post will choose this action, and so this will be, not a very good payoff, but that's what happens. That's the penalty you receive, and so you will get this Nash equilibrium. And now the point is that if you have an iterated prisoner lemma, so this is, there's a lot of literature on this, also a lot of experiments on this, then of course you can see that if player A plays always C and then repeats that, and here this is, twice C in a row and then n times repeated, then you get this kind of payoff. This is when you cooperate, this would be this payoff, in this case, this one. So that would actually be, much better than the payoff that you would receive with this one. But of course, you could also say, well, why not pick this, alternate between these two? And well, that's why, in addition, often this inequality is used. And there's a sort of a very rich literature on this kind of thing, where you have tournaments where people have different strategies for playing, and then the idea is that you may, in fact, you have sort of infinitely many strategies, and that's why, in fact, it's not very easy to even talk about the notion of Nash equilibrium. Well, you can talk about it, but in fact, it's not yet proved that there is even a Nash equilibrium. When you have an infinite number of strategies exist of Nash equilibria, is not always clear. In some cases it is, but in this case it's not known. And so one of the strategies that's often advertised is tit for tat. So what you do is you play cooperate if the other player cooperated in the last setting. But of course, that was not the final story. Then since then, there's a whole raft of new strategies discovered, which received a huge amount of attention. Now, what instead I'm going to do is to look at sort of how the previous learning rules behave. And so this is of the setting. And so I'm going to, so if you look at this memory loss and you take the soft max, then you get actually this dynamics. And again, and this is the point I wanted to kind of make here. Well, this actually is the replicator system. And this is the, well, it turns out some kind of exploration part. One can say this is some kind of entropy term. And when T is infinity, then of course this part is kind of, absent. And you see the matrices A and B, I don't even play a rule, which is not surprising because after all you play, actions with uniform probability. Whereas if T is roughly 0, then in fact this term is not so relevant. It's kind of this part that's, by far dominating. And so you see one type of connection with the previous type of dynamics. And so, in fact, if you take this particular iterated prisoner lemma game, in fact, you still will go to the fact case, which is, and if you take the Sato learning, you will have a similar thing. Now, let's, by comparison, oh, and here's a rock, paper, scissors game when you, look at the solutions. So this is, you can see this chaotic switching that, happens here, and this is the kind of thing that we were able to make rigorous. But now let's look at what happens when you take absent greedy choices. Remember, this was where you take the best response, but a convex combination with some uniform thing. You also get a differential equation, and I'm not going to discuss this in depth because there's a whole story behind this thing here. But here there's different differential equations, depending whether this number is positive or so the difference between the components of Q are positive, or the dependent of this one are positive. So this is when you're, this number is positive, you choose between these two according to whether this has positive or negative sign. And this epsilon 0 and epsilon 1 are here epsilon and 1 minus epsilon. epsilon was this term in this epsilon greedy thing here. And now, and this is sort of like a picture of it, which maybe, there's a sort of story which I'm not going to discuss. But I'm going to really discuss a little bit here what happens in that case. Well, it turns out that actually there's seemingly some kind of very chaotic motion. And I've drawn here the attractor of this thing here. So what happens is, you see the solution kind of going up, and it goes up and goes like this, and then here, and it goes down here. And it seems to happen all over again and again. And well, I mean, we haven't actually proved this rigorously yet. But in fact, there is some kind of, this is definitely, the smooth system. So there is some kind of, like a Filipov system. Filipov system is where you kind of meet, a boundary, and then after hitting that boundary, you kind of move in a different direction. So this is in the R2. Well, in the Filipov system that we have here, in some sense, we have a higher dimensional version of this. So we have here, and in fact, the solutions kind of move across this, but in a very intricate way, which is partly completely understood. Some of this picture we completely understand, and some of it we do not understand. And certainly the global thing we don't understand. In fact, as a side comment, this kind of behavior precisely also happens in the fictitious play dynamics and the best response dynamics. So again, there is this kind of connection. And there's another kind of funny stuff is that if you change the coefficients of this matrix A little bit, well, in this case 4 to 5, but it doesn't have to be that much. It turns out that in fact the solutions go to the defect thing, and the question is why. So this is really something we do not really understand very well at all. So let me sort of give now the overall conclusion of this talk. Well, the first thing that I want to kind of mention again is that each of these dynamical systems have some super interesting chaotic behavior, and it's just a very rich source of class of systems that has not been studied enough by the dynamics systems community. I mean, some of them have also a different flavor because they're piecewise continuous. But in fact, nevertheless, there's a lot, so a lot of the cases where we really understand something are sort of very artificial, or they have some, some piecewise, nice, like in a horseshoe, or you have something very local, or you do it by some kind of perturbation analysis. Or maybe, in my case, that's probably the area that I've worked in most, where you have some additional structure, like a one-dimensional structure, or maybe a complex analytic structure, or maybe a symplectic structure. This is often what you actually need, some extra structure. Now, here's, I think, a class of systems where I think a lot can be understood, but actually not enough effort has gone into that. So, to my mind, that's the first conclusion. There is sort of this rich source of examples that the dynamics community should really study more. The second, for me, very important observation, also surprising, was that actually this having a complicated attractor is often good for players. It turns out that actually, even though maybe from a point of view from an economist, they like to say, well, this is the prediction, you go to this Nash Equilibrium, and that's what happens, and if it's not, then it's somehow not fair. But of course, and if it's periodic, then of course you say, well, it's sort of business cycles or something. But actually, maybe the players should embrace this complicated behavior. The learning methods are very simple, and the payoffs in a way that we can actually make quite precise is actually quite often much better than playing Nash. Now, the third thing is that, a slight change in these learning rules can make a huge difference. Now, of course, from a dynamical systems point of view, it's not so surprising. But if you're from the machine learning community, that looks often surprising, and often people have a very ad hoc approach to it. Say, well, this parameter doesn't work. So we just take another parameter. And I think to have a more, comprehensive and more, more systematic way of understanding that would be super helpful. And then, in fact, the other thing is, which for me was actually also, a surprise to what extent that happened, is you have these different learning rules, reinforcement, replicator dynamics, fictitious play, and they're all kind of quite connected. For example, there's this connection A between fictitious play and replicator dynamics. And I mentioned already one direction was kind of known because, averages of one play of these ones kind of shadow orbits of this one. And there's also a reverse implication, which is following from some sort of inverse shadowing argument. There's also a connection between fictitious play and reinforcement learning. And yeah, that's actually something that, partly because there is sort of this, particularly if you choose this absent greedy approach, it turns out that there's a sort of quite close connections, and I don't think they're understood well enough. And between these two, well, there's actually, this was not so new. If you take some kind of softmax thing, then actually this was kind of observed already in the 90s and revisited by a lot of people. And I just mentioned a few people here, but there's a lot of people who understood that actually if you take reinforcement learning and you take some kind of continuous version of it, then in fact there is a replicator part of it. And I suspect that even if you don't take the time node to 0, there's still a part in the replicator dynamics if you take a discrete version of this. So I think this was really where I wanted to end. And well, thank you very much for listening to this. And I hope that we will have a very interesting stream of talks and that we all learn from each other in this sequence of talks.
Right. Yeah. Thank you very much. Amel, did you want to talk about what you had in mind for the reading group? Are you here, Amel? Yeah, I'll post the slides on the website here. Yeah, we can't hear you, Amel. I don't know if you are talking. No, we cannot hear you, no. Yeah, okay. Yeah, he said that, yeah, so maybe we can answer questions while he's fixing his microphone. Yeah. Any questions? I mean, Goncalo, did you want to talk to ask your question directly?
Hi.
Hi.
Love to see your talk. So for non-economists, is there any kind of good reference where people could get a longer view on what type of equilibrium concepts for games are out there and different approaches and so on?
Well, I'm not a game theorist, but I have sort of looked at some of the. So yeah, there are actually quite a few papers. I think I could send you some references. I mean, the most well-studied ones and maybe the most well-known ones are the ones that I hinted at. Mm-hmm. It is the correlated equilibrium and the course-correlated equilibrium. And the idea there is very much that in the game theory community, they realize that if you have this kind of saddle behavior, you have Nash equilibrium, but this Nash equilibrium could really underperform. Mm-hmm. And then the idea is that often you have some kind of intermediator who says, well, okay, it stops squabbling, I will throw a coin, and it's your own interest. So this is sort of the underlying kind of notion. If you send me an email, I can send you some references from okay. But I also included some of it in my lecture notes, which I have in Imperial College. So I can include that also.
Are these lecture notes available?
I think they're actually on my website.
Okay, super.
So if you look at my website on the teaching, I think you'll find the lecture notes.
Okay, thank you.
Yeah, all right, thank you. I mean, Robert, did you have a question?
Yeah, sure. Thank you, Sebastian. That was a wonderful survey of lots of interesting things. So I guess the big question is, it's obviously about learning, but what morals do you have for machine learning?
I'm not sure whether, I have any morals for machine learning. But to my mind, machine learning is mainly about learning, data. I mean, you have sort of a data stream, and the data stream has no structure a priori. Now here, I think the data stream that you have, which is maybe the payoff or the thing, it comes from a very particular context. And if you ignore that, I think you make a mistake. So to my mind, this is really the point, that these are, machine learning is a big subject. And of course, some of it is sort of an upgraded form of just doing sort of linear regression. And some of it is, something much more subtle. And, there's a lot of different parts. But these are things targeted towards an idea where you have a strategic environment. Now, this could be even in the case where your opponent or your friend that you're playing with could be nature. Your nature could be playing, and for example, this is what is often done also in reinforcement learning, that the nature is doing something, or maybe no regret learning, and that's also done where you play against the nature, and then you want to have some kind of optimality idea. And the optimality idea, I think, stands kind of crucial if you take this point of view, that you actually want to have some kind of notion of what's good. And, so this is why they have this notion of correlated equilibrium or coarse correlated equilibrium or Nash Equilibrium. Otherwise, in some sense, it's just learning something without having any kind of model of what it is that you're kind of trying to improve on. So, I mean, to my mind, that's it. So I don't really think that in the broader thing of machine learning, I don't think I have sort of, but in the idea of strategic environments, which I think is a very common thing, that people try to optimize something, then I think these are very natural things. Of course, people also have, if you look at the literature for iterated prisoner lemmas, they try all kind of other things, but always there is in the background the things that I discussed also.
Thanks.
Thank you. Any other question? Yeah, I'm not sure if you managed to fix your microphone.
Hi, can you hear me now?
Yeah, we can hear you now, yeah.
Okay, perfect. Thank you. And thank you, Sebastian. In regards to what's coming up, as Sebastian mentioned, there's been the work from the dynamical systems perspective on this area is sparse, but there has been work. And we'll be looking at some of the more recent results from people such as Georgios Polaris, as Sebastian mentioned. But other pieces of work include those from Steven Strogatz looking at issues of evolutionary dynamics. There will be talks looking at each one of those. We'll also look at the lecture notes that you have shared in the chat as well, to cover some of the more foundational results in this area, as well as Sebastian's own results in fictitious play and the issues of payoff performance that he mentioned in the talk. We'll keep you all updated regarding when these talks are scheduled. I'll obviously be liaising with Boomer Dien, who, as he's mentioned, if you want to join the reading group, then send him an email and we'll keep you updated as that progresses.
All right, okay, thank you, Ahmed. Yes, as you mentioned, I mean, if you want to join the reading group, I mean, just send me an email to the email address I put on the chat, and then we'll coordinate and find the time that suits everyone.
And of course, if there are any specific areas that you'd like to look into, then also do mention those, and I'll be sure to incorporate them as well.
Yeah, okay. Any other questions, comments? Yeah, all right then. Thank you again for coming, and then take care everyone, and then see you in other talks. Yeah, thank you. Bye-bye. Thanks, bye.